Hello there. Today is August 19, 2025, a fine Tuesday. It's me, Nanom, and today I'm digging into the archives to introduce a fascinating trending paper. Lately, I've been really into how AI is trying to mimic the human brain. And this one, oh, it's a real gem. Let's dive right in. The title is Representing Speech Through Autoregressive Prediction of Cochlear Tokens. The cool is the update called the 20,598 file. It's long, so let's break this down. The big overarching problem this paper is trying to solve is, how do we make an AI that understands speech as well as a human? I mean, think about it. We humans are amazing. We can pick out a friend's voice in a noisy cafe, understand if someone's being sarcastic just from their tone, and recognize words effortlessly. Getting a machine to do all that flexibly, efficiently, that's a huge challenge. For a while now, there have been a few main ways researchers have tackled this. One way is with something called neural audio guardians. You can think of them like superpowered audio compressors. Their main goal is to take an audio signal, squish it down into a compact code, and then reconstruct it perfectly. But, the paper points out something interesting. Our brains probably don't work that way. We're really good at ignoring unimportant details. Like the exact pitch of a vowel or a little bit of background noise. Perfectly reconstructing the sound wave isn't our primary goal. Understanding the meaning. Then you have these predation-based models like the famous HuBERT. These models play a sort of play in the blanks game with audio. They'll mask out a little chunk of speech and try to predict what's missing, using the context from before and after. They're really powerful for sure, but their methods can get pretty complex. And a third approach is contrastive learning, used by models like WavCoch. This is kind of like teaching by comparison. The model learns to pull representations of similar sounds closer together, and push different ones further apart in a sort of virtuous space. The catch is this often requires a lot of human-defined rules, heuristics, to decide what counts as similar. Plus, having a model compare thousands of audio snippets all at once is, well, probably not how our brains are wired. So that's the landscape. You have models that are too focused on perfect sound quality, or use methods that are very brain-like. This is where AuriStream comes in, and oh, this is the cool part. The researchers decided to take inspiration directly from human biology. AuriStream is a two-stage framework that mimics our auditory system. First, there's a stage called WavCoch. This is basically the model's area. It takes the raw audio waveform, and instead of just analyzing it mathematically, it transforms it into something called a cochleagram. This is a representation inspired by the Cochlea, that spell-shaped tube in our ear that turns vibrations into noise signals. Then, they choose something really clever. It causes this backcochleagram into what they call cochlear tokens. Imagine turning a smooth, continuous sound into a sequence of digital codes, almost like an alphabet for sound. It's super efficient, generating about 200 tokens for every second of audio. Okay, so that's there. The second stage is AuriStream itself, which acts like the brain. It's an autoregressive model, kind of like the gut models we hear about all the time. And its job is incredibly simple. It just looks at the sequence of cochlear tokens and tries to predict the very next one. That's it. No complex reconstruction, no comparing thousands of samples. Just a simple, elegant prediction task based on a brain-inspired input. So does this vibrant-inspired, simple approach actually work? Yeah. The results are pretty stunning. First off, AuriStream is really competitive with the big, state-of-the-art models on tasks like identifying phonemes, which are the basic building blocks of words. But where it really shines is in understanding lexical semantics, which is a fancy way of saying it gets the same meaning of words. There's a benchmark test where a model has to judge the similarity between word pairs, like knowing that the water and river are very similar, while the festival and whiskers are not. Right, a pretty common sense thing for us. Well, AuriStream achieved state-of-the-art performance on this task. This suggests that just by learning to predict the next sound, the model is actually learning deep relationships between word meanings. It's even cooler though, is that AuriStream isn't a lightbox, because it predicts these Cochlear tokens, which can be turned back into a legram image. You can actually visualize what the model is thinking. You can give it the start of a word like the lasham sound and watch it predict the rest of the word washi. You can even give it a few seconds of speech, and it will generate a plausible continuation of what might be said next. And you can convert the generated back into the audible sound. It's not designed to be a speech generator. The fact that it can do this is a fascinating side effect, which says it's truly learning the statistical structure of human speech. Now let's think about how this could apply to our everyday lives. Here are a few examples. First, think about lightbots in dialogue systems like your voice assistant, because AuriStream is so good at understanding word meanings. An assistant built on this technology could grasp the nuance in your request much better. You might to get some water? It might be better using context to figure out if you mean a drinking fountain, bottle from the fridge or nearby lake, because it has a more human-like grasp of how these concepts are related. Second, in the field of information extraction and summarization from audio. Imagine you have a 2-hour recording of a company meeting or a university lecture. A system using AuriStream could create a much more insightful summary. Instead of just transcribing the words and picking out keywords, it could understand the underlying semantic things being discussed. It would give you a summary of the core concepts, not just the most frequent words. And third, this could be huge for machine translation of spoken language. When we talk, so much of the meaning is in our tone and emotion. AuriStream has shown strong performance on tasks like emotion recognition. So, a real-time translation app using this kind of model could not only translate the words you're saying, but also capture the intent behind them. It could translate a sarcastic, "That's just great," into the correct sarcastic phrase in another language, which is something current systems really struggle with. When you compare AuriStream to other technologies, its uniqueness really stands out. Compared to models like HuBERT, it achieves amazing results at a much simpler and more biologically plausible objective. It doesn't need to look forwards and backwards in time. It just predicts what's next, like we do. And compared to neural networks that focus on perfect audio quality, AuriStream's philosophy is different. Its goal isn't passive reconstruction, but lending a rich, meaningful representation of speech for understanding. The combination of its Jude imprint and its simple predictive brain makes it powerful, efficient, and wonderfully transparent. So in summary, this paper introduces a really elegant framework. It's a big step towards AI that processes speech more like a human. It shows that sometimes taking inspiration from the elegance of biology can lead to simpler, more powerful, and less mysterious AI. Of course, it has limitations, but was mainly trained on English-read speech. But it opens up exciting new directions for the future. This is a really fun one to explore. That's all for today. This is Nino signing off.